A rock is dropped from the top of a tall tower. Half a second later, another rock, twice as massive as the first, is dropped. Ignoring air resistance, which one of the following statements is true? We can go through them one at a time and determine their validity. I've also included kinematics equations and the kinetic energy equation here for reference. So let's start with the first statement. They strike the ground more than half a second apart. So in the question, we're told that half a second is the difference in release time of these two objects. So our first statement is saying that the second, the time between them hitting the ground is going to be larger than the time between them when they were released. To analyze this, we can use one of our kinematics equations. Specifically, d equals VIT plus 1/2 AT squared. Now, the d for distance here refers to the distance that these objects fall, or the height of the tower. We know that the two objects are released from rest, so our initial velocity is 0. So we lose that term, and we're left with d equals 1/2 AT squared. Now let's solve for t, and then I'll explain something here. So we multiply both sides by 2 and divide by a. So we have 2d divided by a, and then all inside a square root. Now what this equation here is describing is t is the time it takes to fall distance d, the height of the tower, under the acceleration a, which is the acceleration due to gravity. Now nothing in this equation talks about the mass. Nothing in it says that the time it takes to fall, t, varies with the mass. There's no mass in this equation. Therefore, since they're released half a second apart at the top, they will hit the ground half a second apart as well. That time to fall isn't going to change. So the statement that says they strike the ground more than half a second apart is false, since they'll strike the ground exactly half a second apart. Let's look at the third statement now. The acceleration is greater for the more massive rock. Well, that's just not true. We can look at multiple equations to explore this question. We could look at just the force due to gravity, which is mass times gravitational acceleration, g. We see that both rocks, no matter what mass they are, will have the same acceleration on them. That is the acceleration g due to gravity. And the force on the objects changes with their mass, but the actual acceleration is not greater for the more massive rock. It is the same. So that statement is false. The fourth statement says they strike the ground with the same kinetic energy. Well, if we look at our kinetic energy equation, Ke equals 1/2 mv squared, the kinetic energy is dependent on two things, mass and velocity. And the objects here have different masses. One has mass m, one has mass 2m. And to say that they strike the ground with the same kinetic energy isn't true, because one of the masses is doubled, which will then in turn double the kinetic energy. So that one is not true. The last statement says the speed of both rocks is constant while they fall. We should know just from intuition that that's not true. Since they are under gravitational acceleration, they are going to speed up. They are going to accelerate, and their velocity will increase as they fall. We can look at one of our kinematics equations to explore that. Specifically, the Vf equals Vi plus At. Well, their initial velocity is 0, so we lose this term. And we're left with the equation, the final velocity or say the velocity at any point besides the very beginning, is equal to the acceleration due to gravity times the time. And so we can see that as time increases, the velocity of our object will increase. And since time does move forward and it does increase as an object falls, the speed is going to fall up, and therefore the speed or the velocity of the rocks is not constant. That leaves us with our final statement, which is the true statement. That is, the distance between the rocks increases while both are falling. And this is true. When we release the rocks, initially the mass m first, we know that it's going to begin to fall. And it's going to have some distance. It's going to have fallen some distance before the second rock is released. But at this point, the velocity of mass m is much bigger than the velocity of mass 2m when m has been falling for a while and then 2m is just released. And so the distance between the two rocks is going to be increasing, since the mass m is going to have a higher velocity than the mass 2m at all times besides at the very bottom. So the distance between them, therefore, will increase.